recording. We're good to go there. Good to go there. All right, let's start with questions.
So, it's not really a question, well, kind of is, but do you need to put a main function inside of main.h to execute the prototypes, or can I just only put in the prototypes?
Only put the prototypes in main.h. Don't put a main function inside there.
Okay. So I'm getting some kind of like error where it has like an undefined reference to the log function.
So when
I put in math.h inside of main.h, but it doesn't work for some reason.
So when you compile, make sure you say -lm at the end of the GCC command.
Gotcha.
And that says.
That. I don't know why that's a thing.
Yeah, I know, right? It's only pops up once in the blue moon for what we do, and this is Blue Moon Day.
You gotta use it for other leaking in other libraries too. But
If we use other libraries, like if we use DBM later in the course, then you need to do a -l GDBM and things like that. But for most of what we end up doing in the courses in this sequence, we end up just using kind of the standard stuff that's linked in by default or available by default. All right, other questions? So if you find that you're not able to finish your stick program the way you would like by 8 in the morning, my suggestion is, get as much of it running as possible. Get the basic gameplay running and start, adding extra features to it and so on. But if what you turn in will compile and will start to, yeah, I meant high-low, not stick. Thanks. If it will compile and it will run the basic game loop, if the user plays nicely, for example, that gets you a lot of points, right? If it's almost complete but it doesn't compile and I can't run it at all, right, then that's harder to get partial credits on. So it always pays in courses to do some strategizing on grades. You don't want to totally gamify college, right? But at some point, you are getting a grade for stuff you turn in, and it's sometimes worth, doing those calculations and say, okay, I really, really think I can get this to work, but, until I get it to work, the game seg faults when I start. So I'm going to comment that out of my program, and I'm going to, make a submission comment saying, hey, this is almost working, but, I commented it out. That kind of thing. All right. Well, let's continue playing with GDB. So we started digging into this yesterday. Oh yeah, send me an attendance note. Let me know who's here. So we started playing around with GDB yesterday, and I posted on Canvas a really short, kind of half a page synopsis of the commands that we're going to be using for this. And you can find very large pocket guides. You can find entire books on GDB and so on, but we're not going to get that sophisticated with it. And so this is more than what we're going to use. Basically, compile with -G, use GDB to start running, say start to begin your program, list your source code, print the value of a variable, step into or step over, make a breakpoint, and continue until you hit another breakpoint. And we'll play with finish in a bit. And that's probably most of what we'll be doing. But let's play with some specific examples. So, and again, these have bugs in them, so if you see the bug, you know, that's good. You're ahead of the game in debugging, but we're going to try to find these bugs through GDB. So here's another another try at, you know, our main program calls count E, should return a number 2, and there's my usual loop. I initialize my count to 0, so that won't be a problem. And so if I go ahead and I run main2, it tells me result is 0, right? So it's not counting my E's for some reason, even though, you know, I'm in my loop. I'm checking to see if it's equal to an E, and if it is, I'm incrementing my count. So so let's run this in GDB and try to figure out what's going on. So I'm going to do gcc-g, and then output main2 and then GDB main2 told me that it read symbols. Sorry?
Can you make a debug flag and make for that?
Yeah, you can actually. So since we're doing make files anyway, let me get you a good example. So you can set up symbols inside a make file. And so typically you have a symbol you would define at the top, like GCC flags, right? And then you could use those inside your make file. And so if you wanted to compile with debugging, you would just set that variable in the top of your make file to be -g. And then if you don't want to debug, you just set it to be, you know, blank. And I have a sample of that somewhere. I actually don't remember the syntax for that. So on the top you can say something like $ parentheses C flags equals -g, which no, let me do that differently. C flags equals -g, and then when you compile, you should be able to say, you know, GCC $paren C flags -o or -c, or whatever else you do, and this should get replaced with that. So then if I change my make file and just say C flags equals nothing, then this will just do a plain GCC without that. And that's probably the easiest way to turn debugging on and off, because you only have to set that in the top of the make file instead of going through and changing it on 5 or 6 GCC lines. All right, so we're inside our main program, and let's play with breakpoints. All right, so I know that I can step my program, and I can, you know, get down to this statement, and then I can say step to go inside count E and so on. But I'm just going to say break at the function count E. So I'm setting up a breakpoint, and it says, hey, when you get to line 14, that's the first executable line in this function, let's stop. And now I'm going to say continue, and continue is how we tell the debugger to keep running until you hit a breakpoint. Right? So remember, when we say start, it tells us there's a temporary breakpoint. I don't think I said start yet. So we say start, there's always a temporary breakpoint in the beginning. So I'm just going to say continue, and it will run until it gets to the breakpoint I said, which was the beginning of the count E function. Alright, so count E is called, it's got one argument, which is the string hello bye. We're going to initialize C to 0. So I'm just going to start stepping through my code. I'm going to say for I equals 0, I less than string length arg I plus plus. I'm going to say if arg bracket I equals E, well, if I look at arg bracket I, it should be in uppercase H. So this if statement will not execute. And guess what? The next statement is a return. And if I print the value of C, C is equal to 0, well, that's why my result was 0. Because I returned right away. Well, why did I do that? Arg has, 9 or 10 characters in it. I should go through this loop 9 or 10 times. So let me say next. And that's it, I'm exiting my function. So take a look at your count E function again. And what's the problem here? So anybody see the issue?
You have open parentheses C close parentheses right after the return.
Mm-hmm.
Oh, your return's in your for loop instead of outside.
My return is in the for loop instead of outside. Right? And that's pretty clear from stepping through in the debugger because, I did the first thing in the for loop and I immediately said return. That really kind of like puts in your face, hey, you're returning right after this if statement. Right? But that's hard to see sometimes when you're staring at code and you've been staring at it for a long time. So now we go back and we stare at this differently and we say, okay, here's my if statement. That's where the if statement ends. Oh yeah, there's my return. This is inside the for loop. So that's just a coding error. All right, so we could go ahead. We could fix that and try it again. All right, let's try another one. So here's main3.c. And my return is outside my for loop this time. So we'll compile this, we'll run main3, and it tells me my result is 0. So let's gcc-g, and let's gdb main3. So we'll start it. I'll go ahead and step into my count E function. I'm calling count E with hello bye. C is equal to 0, so that's good. I'll say for I equals 0, I less than string length arg I plus plus. If arg I is equal to E, and it's returning. So there's something weird going on here. And if I look at C, it's a 0, well, it hasn't counted any E's. But if I think to look at I, that's going to give me some information. I is equal to 9. So there's clearly something wrong in my looping here. And the behavior was, I did my for loop, I did an if statement, and then I returned. Even though my return is inside, even though my return is outside of my curly brackets. but it looks like it didn't loop. So does anybody see something going on here?
I think you forgot a curly bracket for loop, correct? No?
Well, I got a curly bracket here.
Oh, okay. It's just the way it laid out kind of throws me off.
Yeah.
Behind the if statement.
Say again?
The curly bracket's hidden behind the if statement. Just because of the way you build it. Looks like it's missing.
Sort of. Let's run this again.
But that's not the issue.
Let's run this again from the start. So let's step inside the count E function. Let's say next. So we haven't done our for loop yet, right? I has got its uninitialized value. I'm going to go inside my for loop, and suddenly I is equal to 9. Even though I said start I at 0. This is a really, really subtle bug. So this is the culprit.
Is it because I is equal to the string length, or is less than the string length?
I ended up being equal to the string length. Hello space BYE, that's 9. But this semicolon is basically saying, don't do anything inside the body of the for loop. That ends the whole for loop.
Oh, that is sneaky.
Yeah, that's a really annoying little bug to try to find. But that semicolon basically says, you know, I have one thing I want to do in the for loop. It comes between the parentheses and the semicolon while there's nothing in there. So it loops through really fast from 0 through 9, doesn't do anything, and then it's done with the for loop. So now we have an if statement and a return statement. And these curly brackets do not cause it to loop. They just are there, they don't do anything. So that's one, even with GDB, it can be hard to find. So go ahead.
Useless parentheses like that won't throw errors.
No.
Weird.
Yeah, that's either a feature or a bug, depending on what day it is.
But definitely got the languages.
Yeah. So C is very much, you know, happy to do whatever you ask it to do. Which can be good or bad. Alright, but, you know, going through this in GDB, it may not explain that that's the problem, but it really kind of forces your attention to, you know, something is going on right here, because it's not doing my loop, right? I set I to 0, but the next statement I is equal to 9, and then it returns. Alright, so let's try main 4. So main 4, I do not have my semicolon there, so that's good. I'll just go ahead and compile with a -G, because I know it's going to break anyway. So it tells me my result is 10. So let's step into the count E function, and I is equal to 0. And I've got a for loop for I equals 0, I less than string length arg I plus plus. If arg bracket I is equal to E, well, it's not, it should be an uppercase H. So it'll skip that if statement. We'll increment I, so now I is equal to 1. Arg bracket I is equal to E, so this if statement should fire, and it should say increment I. And now I is equal to 2. So something's wrong already, right? Because I should be equal to 1 because we just found 1E.
Should be incrementing a different variable.
Yeah, it should be incrementing a different variable. I'm using I for both the loop control, but also to count the number of E's. and that's just begging for confusion. So you know, I should have like integer count equals 0 and then increment count and then return count. All right. So here's main 5, and I've added a debug statement in here because it wasn't working. Yeah, isn't this a fun game? This is what I get to do when I grade sometimes. So I've added a debug statement in here. So let's do main5.c. I'll do the -g switch. And main5, we're still counting hello bye, so it should return a value of 2, and it returns a value of 9.
And what is the -g again?
That tells it to go ahead and include information for GDB.
Okay.
And so this, you know, it found 2 E's. It printed out found an E exactly twice. But for some reason my result, my final count, was equal to 9. So I'll come in here, my count is 0. I is equal to 0. Arg bracket I is should be my uppercase H, so this if statement will not fire. But I'm saying count equals count plus 1. And now count has been incremented to 1, even though I didn't see the letter E. I is equal to 2, arg bracket I is equal to E, so it told me it found an E, that's the E in hello, and it incremented count, so now count is equal to 2. Now I is equal to 2, and arg bracket 2 should be my L, so the if statement will not fire, so it doesn't print anything, but it still increments count, and now count is equal to 3. And so it's incrementing my count every time whether or not I find an E. So what's going on?
After your if statement.
Say again?
No parentheses after your if.
Yeah, no curly bracket after my if statement. If you write an if without a curly bracket, it includes a single statement in the if. In that case, it's this print statement. This is actually outside the if. So it's if arg I equals E, print this, and then regardless, go ahead and print count.
So like if statement without a curly bracket, just only will run the next line and that's it, right?
Yeah. If I put curly brackets around both of these, then both of these would be conditional on this statement being true, which was what I wanted to have happen. But if I forgot it, then only this is conditional. And this happens sometimes if, you know, you're building up your code, maybe you're not trying to do the count yet, you just want to print out when you found an E, and so you don't have this statement in here, and this looks like it works great. It'll print this message out twice, and then you go ahead and you add the count message, and it's not working, right? And so this is where habits, like, you know, always using curly brackets, even if you only have a single statement, those kinds of habits can save you down the road. Alright, one more of these, main 6. Got my curly brackets around my if statement this time, so count should be equal to what we want. And this one I changed it to ask the user to enter a string and then call count E on that. So I'm going to do main 6 and I'll say hello test. And it tells me it found 11 strings, 11 E characters. Alright, so I'm going to run this. I'm going to put my break at count E. And I'm going to say continue, and it'll say enter a string, and I'm going to say hello test. So now I'm in my count E function. My argument is this string, hello test, with a new line. We can see the new line there that f gets added to the end. My count is initialized to 0 for I equals 0, I less than string length arg I plus plus. If arg bracket I is equal to E, and it's incrementing count plus 1. Alright, so let's see what's going on. So when I is equal to 1, arg bracket 1 is an E, so this if statement should execute. But let's take a look at it now. So I is equal to 2, print arg bracket I, that's the letter L. L is not equal to E, this if statement should not fire, but apparently it does.
Is there any way you can go back to the actual code?
So there's the count function.
If statement has a single equal sign.
If statement has a single equal sign.
Oh yeah.
And if I was really stuck and I kept scratching my head, I might try to double check and say, let's look at arg bracket I, and I'd see, oh, that's an E. Wait, why is that an E? What is arg equal to? Oh, okay, and now it's pretty clear, right? My string is being changed, so then you got to figure out why that is, and eventually, hopefully, it brings you to, yeah, that's a single equal sign, so it's actually assigning a value, and then this has the value E, which is not 0, so this if statement is true, so it's always incrementing count. Cool. All right. So those are you know, sort of particularly slippery bugs maybe to find, but that's the process of GDB. And it takes, you know, some practice, some trial and error to get better with this, but the more bugs you find, the better you get with GDB, which is another way in which, you know, finding bugs is a happy event, because it means you're going to get better at debugging on the other side of it. It's just not happy, you know, at 3 in the morning with a deadline looming, but it's a really important skill, right? So debugging is one of the 3 things that I claim make excellent programmers, really good debugging skills. Because you're going to have bugs, right? Sometimes because you introduced a bug because you're human, sometimes because you had an imperfect spec that you were working from, or you know, you're interfacing to another piece of code that has something glitchy in it, or because something changed over time and now this thing that should have worked one way works a different way. And so the better you are at debugging, the more successful you'll be in programming in general. All right, another thing we can do is we can set up watch points. So if I say watch count, I can say continue, and this will run until count changes, and it will tell me, hey, count just changed, the old value was 3, the new value was 4, and now we're about to execute this for statement. And so if, you know, you've got some chunk of code and at the beginning this variable has a value you expect, and somewhere between there and the end of the function that value changes in a way that you don't expect, you can say watch that variable, right? Just say watch in the name of the variable, and whenever it changes, you'll come back to the debugger, it'll tell you what the old and new values were, and if those were the correct change you expected, you can just say continue, and the next time it changes, it'll stop and tell you, and so on. So if I was using my original test program where I just had, you know, a string hardwired in here, and I try to run this program, I get a seg fault. And that's a little unexpected. But again, if you compile it with a G switch and you GDB it and you say start and just tell it to continue, you'll get some good information about where that seg fault is happening, right? It's telling me right here there's a seg fault at line 18 of main 7.c. Here's the statement it's trying to execute. And it's like, why is an if statement giving me a seg fault? Well, let's print I is 0, let's print arg bracket I. I can access that, there's no seg fault. Why am I getting a seg fault? Well, if you're getting a seg fault, you're trying to do something with memory that you're not allowed to do. Either you're trying to read something that you don't have read access to, or you're trying to write something that you don't have write access to. Well, I just confirmed that I have read access to this location, because I just printed the value. So the problem has got to be that I don't have write access. And that kind of forces you to say, why does this think I'm trying to write something? Oh yeah, that's where the single equal sign is. I'm doing an assignment. And this string, hello, bye, is stored in an area of memory that I do not have write access to when I'm running. And so that's what the seg fault's about. And it's basically throwing a seg fault to kind of save you from yourself, right? This string, we're setting it up as a constant. And since we're saying, you know, this is just a fixed string, the linker is putting this in an area of memory that's read-only, so that if something tries to modify it, instead of changing it, we'll go ahead and get a seg fault. So that's actually a feature. All right. What else do we want from GDB? We got watches. Let's talk about memory.
Well, can you explain about how does the segmentation fall again? It seems like you're storing a string inside of a integer, which is by assumption the reason why it's not.
It's
not letting you access that memory.
So it's okay to be storing a character inside this location. The problem is this location is not writable. It's an area of memory, this location right here, that the system set up as being read-only. And when we try to do an assignment, we're trying to write into a memory that's write protected, basically. And that's one of the two main cases where you get a seg fault, trying to write something that's read-only.
Okay. Can you show me like how to fix it? Just so I can understand about what to do if I went to this kind of segmentation fault?
Well, it's just a matter of putting two equal signs, isn't it? It's a matter of doing a logic test versus an assignment, right?
Yeah, so the problem with this code was that we had this single equal sign, which is mistakenly trying to assign a value to this instead of compare a value. So the bug is not that the memory is read only. The bug is that we're trying to write that memory mistakenly.
Is the reason you can't write it is because strings are passed as pointers?
Well, strings are always passed as pointers, but for example, in this previous version,
Oh, it's hard coded.
it's hard coded.
Okay. Interesting. So if you had set it using an fget, it would be fine. Just like
Right, which is why in that previous version I used an fgets. So here we're calling our county function, but our string hello is stored at this location. 7fff blah blah blah. That's generally an area that is readable and writable. That's in an area of the system called the stack. Whereas this is a totally different memory location. It's a location that's set up to be read only. Now, we don't usually need to do this for this course, but we'll definitely do this a lot in 222, which is looking at memory directly using GDB. And so there's a command called X. And we can say X followed by an address and look at the contents of memory. And so, for example, if I say X and I type in this address, right, this shows me the contents of the machine's memory starting at that location. And there's a 6C, a 6C, a 6.5, a 4.8, and so on. Well, 48 hex, that's the ASCII code for an uppercase H. 6.5 is the ASCII code for a lowercase e. 6C, 6C, those are each the ASCII code for a lowercase l. And if I examine the next location, 6F, that's an ASCII code for an O. 0A, that's an ASCII code for a new line, character N, \N. And then 00, that's the null terminator. So these are the actual bytes that comprise this string. And when county was called, it wasn't called with this string as an argument, it was called with this number as an argument. But the code inside count E uses this number as an address where a string is stored. And so the code will go to that address and start pulling off bytes from there until it gets to a null terminator, and it'll say that's my string. And we could examine, 20 locations starting right here. And there's whatever happens to be in memory. I could say examine as 20 characters, and so there's the character versions of what's stored in memory. HELLO, new line, bunch of zeros, a bunch of things that don't seem printable, and so on and so forth. If I try to examine location 0, it says I can't access that. Right? 0 is not an accessible location. But if you just kind of put in random addresses, you can probably access them. This is a lot of zeros. And this is stack space. This is just stuff that happens to be in the memory.
Can you look at some heap space?
Say again?
Would we be able to look at heap space?
Yeah, if you can find the heap, but I don't know where it's stored. I'm thinking the heap is probably around that 555 location that we had before.
I have it here as like no RAM, and you try to use something that's currently already being used.
So there's a whole virtual memory system behind Linux and other operating systems, so that even if you don't have a lot of RAM, there are mechanisms that make it look like you have more memory than you do. So this address, for example, I think it's 12. Yeah, this is 12 hex digits. That's 48 bits, right? That would only be a thing if I had 65,000 megabytes of storage, so 64 gig, which I don't have. But this address is not a physical address in memory. This is what we call a virtual address. And so we're talking engineering 270 now, right? Your physical memory typically begins at location 0 and maybe goes up to 16 gig if you got 16 gig of physical memory. But when I do something like, say, read from address whatever, that's not a physical address, right? Physical address 0 exists. There's a first location in my DRAM, but if I try to access memory location 0 in the debugger, it tells me that doesn't exist. So there's a mapping between these virtual addresses and your physical addresses. And so some things map to, you know, the higher part of this address space, those things that start with 7F. Some things map to things in the middle, like this. And so this is something, you know, inside my count E function. And some things map to lower addresses. And it's possible that my virtual memory actually has more storage than my physical memory has. I might have, you know, 1 gig of physical memory, and I might have enough virtual memory to represent, you know, 16 gig. And this is where we get into paging, where I'll use, you know, a chunk of physical memory to represent this piece of virtual memory. But if I want to use something from this part, then the physical memory associated with this will get written out to disk. And the memory associated with this chunk will get loaded from disk into the physical memory, and now I can access things in here and map them to actual DRAM locations. And so that's where we get into swap files and things like that. So operating systems, right, which is a course you can take at a university, you can dig into all of this memory hierarchy, and it's fascinating stuff, to me at least. And it's another one of these ways where hardware and software meet, and you know, doing something in machine language like, you know, increment this memory location might not work unless you have an operating system, because if I try to increment a memory location that's not loaded into my physical memory, something has to happen to go to the hard drive and find the swap file and open it up and pull the contents of some chunk of that out and load it into physical memory. Well, that's stuff the operating system does. And so I might, you know, say increment memory location, you know, 200 hex, and in executing this one assembly language instruction, I might cause, you know, 1 million other instructions to execute before this finishes. And so this will generate what's called an exception. It's like a software interrupt. And all this stuff happens in the operating system. Your disk spins and makes noise and all this kind of stuff. When it's all done, the CPU backs up the program counter and says, okay, let's try that again. Increment location 200, and now it works. So you can mess around with all of this stuff in GDB and really kind of like get inside the system and start to understand at a lower level what's going on. We don't do that in here. We will in winter need to look at memory. But we're probably okay in this course with just the other commands that we've learned so far. And this is, you know, runtime library or operating system code. I don't have something called libc, CSU, init, but that exists, right? It's part of the other stuff that gets linked into my program. All right, so that's GDB. This synopsis that's posted on Canvas is probably more than enough. Layout and step I are for fun if you want to do the assembly language. BT shows you your call frame, and deleting breakpoints, getting info on breakpoints.
What's the and sign for P and variable do?
So for example, let me start this so I know where I am. So I can say, let's print the value of temp, that's a string, right? If you do print ampersand temp, that's the address of that variable.
Oh, okay.
Right, so it's the same ampersand from C. and I don't know why this doesn't work. This used to work, but you can run functions basically. Well, I'm in my bad version of county. Semicolons. So I'm printing, you know, things that involve function calls, and that's totally okay with GDB. So you can do a lot of debugging type operations inside here, including, you know, evaluation of expressions and so on.
So
Print 2 times 3.
it's not just specific to string length, right? Like if I made, I don't know, some function that says 2 times 2, I could evaluate that here, right?
Right. And you used to be able to say print string length and actually evaluate that, but that's not working today or yesterday, and I'm not sure why. I'm thinking string length is a wrapper around something else. Right, so I just called the fgets function from my debugger by saying print the value of fgets. Right, and I typed in something because it waited for me, and now if I look at the value of temp, it's that string that I just typed in. All right, other questions? So I think that's all I had to say on GDB. It's one of those things that, you know, as you're writing code, if you're stuck or you're bored, it's fun to mess with. And after you've used it a few times, it should start to feel pretty manageable. It's not a lot of commands you have to worry about, but getting it, you know, squared away just right takes a little bit of getting used to. So you have to compile with a -G switch. You have to remember to say start, and then you can mostly just, you know, say next. But, you know, weird things can happen. If I happen to say step here, that's going to say, hey, don't go to the statement after fgets, go to the next instruction inside fgets, and now I'm debugging my fgets function. Right, I'm inside fgets, I'm at line 37 of iofgets.c. I don't have access to the source code, but I can see fgets was called with 3 arguments, right? The first one is this, which is the address of temp. The second one was 120, that's the length. And the third one is presumably a number corresponding to standard in. And I can even see the names of these variables inside fgets. The first argument is called buff, the second is n, the third is fp. But if I start trying to debug this, it's just going to be weird. So you can say finish to like get yourself out of a function that you accidentally stepped into. So now I'm at the enter a string part, and then I'm back from fgets.
Could you do like a recursion function, or would that get a little weird?
You can do recursion and step through it. It's a enlightening and confusing way to study recursion. Confusing because, you know, you'll lose track quickly of where you are, but you also have this backtrace function that can show you your call frame, and that can actually help. And when you're inside a call frame, you can look at variables in there, but you can also jump to other frames and say, hey, let's go back, you know, 1 frame and pretend that that's the context we're in. And so you can look at the variables as they were before your current call, and so on. So this is just a quick and dirty list I made for my own reference. My suggestion would be, make yourself a copy of this, right? Try these different commands and figure out what they do, and make yourself notes, right? You always want to make notes from classes. and so a good way to make notes on GDB would be to sit down with a file of your own choosing, run GDB, start using these different commands, see what they do. Go back to the video if you have to, right? But explore it, and try it out like that. Or, you know, find a quick reference guide on the web. But most guides you find at GDB are going to have, you know, a lot more commands. So don't get tangled up in them. All right. So tomorrow I want to start talking more about Linux itself. I want to talk about some file system concepts for Linux and start digging into some more of the commands and so on. And then next week we're going to start digging deeper into strings in C. So send me an attendance note, please, on the way out, and I will see you tomorrow.